Hello, guys. My name is Rajit Mukherjee. I'm currently pursuing my PhD in electrical engineering from Pennsylvania State University. So, today I will taking the opportunity out to explain whatever I have understood the math behind transformers, and it's really fun. And it was a really long journey. I slept yesterday night really bad, so I hope you will forgive me with some of my mistakes I do while explaining this to you. But this is so exciting that I can share with you. Like I can wait to share with you. So let's start. So there are a few modules out here. I will try to be as short as possible, and I have tried to keep the math to the optimum level, not minimum. Like I will explain to you how the matrices are working here, okay, and everything is working here, but also not putting all the tough equations out there to make your understanding and delay your understanding. So the math is optimum for your information. So we will start. So one of the problems of reading technical papers. So this is based on the paper called Attention is All You Need." It's a famous paper of 2017 by uh, A- Ashwani et al. Um, and of course, papers are not meant to write so well. So I took this opportunity out to explain to you in my own possible way. I hope it will help you. Also, I want to thank Professor Collins for teaching me the basics of computer vision and teaching currently the deep learning aspects of computer vision. And he has given us this task and of understanding this paper. So I'm taking this opportunity out to share my own personal understanding. Also, probably it will help other students out there who are learning the same. So that's the purpose of sharing it with you. So let's start the discussion. Let's start with asking by asking this question, that how the model exactly works, because it's not exactly, I didn't find anywhere it's explained in the beginning, so I found it at the end. So I think this is the first question which we should address: how the model works. So first of all, I am assuming that how you have the basic knowledge of deep neural networks. Otherwise, you will not understand exactly the intuitions behind it and the motivation of some aspects, some architecture of the whole building up of the um, model. So understand that what is our goal. So you have a word, like you have a sentence, you have a set of words, that, let's say, I have written in my own mother tongue, language of mother tongue. So it's in Bengali, and the word one is onko korte amar bhalo lage, whose in English translation is I like to do math. And so the goal is that if you fit in this uh, sentence, অঙ্ক করতে আমার ভালো লাগে, or word 1, word 2, word 3, word 4, that sentence, that will be transformed into a numerical values, because the function network will not be able to understand this value. So we need to change it in numerical values, and then it will be going through a function which is essentially a network, but the function will also be inputted by some parameters out here, as you have seen, and there'll be some output of the function on the left hand side. This sentence, we want to translate the sentence into the English language. So this sentence will be transformed into this, like, input in the function, which and there'll be output. The parameters are theta e, with the e denotes the encoder. This is called the encoder part. And now this will be given as input into the other aspects, which is called a decoder. Now, there's a very interesting thing going on here, and which I want to explain it to you. And this is very important because the model is, like, the second half of the model, the decoder is based on this. That understand what will happen, that it's if you write I, it will probably give like to, like the next word as. But how to start the whole loop. So that's where it includes two more addition, which called end of sentence and starting of sentence. So which called start and end. So if you input start, the output of the function g will be I. Then the I will be feed in. So then it will be the word one, word two. So first you input the word one, which is the starting of the sentence, and the output will be this word two I. Then if you input word one and word two, that means the sentence has started an I, then it will give output as word 3. And then if you again input it like the word 1, word 2, word 3, that is starting of the sentence I like, then it will give the output, just the output 2. And this will carry on, and when it will be start of the sentence I like to do math, the final output will be word 7. This is how the model will work. Okay, this is how the model will rather learn. The output will be the entire sentence, but this is how the model will learn. This is how the model must learn, because understand, the like, the 2 has nothing to do with the math, so it has to learn in a step by step fashion. And this is a very important aspect of the model, okay, which is fundamental to the structure of the model. So, and to start the output, the starting and to end the output, the ending of the sentence are added, so that it can help you, help the model to recognize that, okay, the model we have to implement this g function now. So how this model is being done similarly, so essentially, on the other hand, like on this red hand side, we have a set of words which is input, which is made as input into the model on the right hand side, and the g, which is changed numerically and then present as input to the model, which is certain parameters theta d, like it's a set of vector of parameters, which is d is a decoder. And then finally the output will be those set of words. So this is a basic algorithm. Okay, this is a basic algorithm. Great. So now this is how the model is working. Now the next question is that, okay, by the way, some extra aspects I should tell you that f and g are composed mainly of linear functions and basic nonlinear functions. Like linear functions means matrix multiplication, and for example, the parameters are matrices. Okay, the parameters are matrices, and it's essentially matrix multiplication, just like neural networks. And the nonlinear functions are really usually. This is because using this you can approximate any function to a certain degree. Great. So we have these two sides of the network, or of the whole function. One is learning about the input sentence. One is learning the input sentence, also the output sentence, and giving an optimum output. Okay. So this is for the training purposes, and this is for the result purposes. Okay, coming back to the next part of the understanding is how the learning is happening here. And this is also similar to the first part, that essentially the left hand is remaining same, but the goal is to learn the parameters theta e and theta d. So how the model is learning is that you are making the model learn by giving inputs of certain phrases. Let's say, as I have told you, the model should learn start, like you should input the model, input into the right hand side of the model, that I like to, and the model must learn that the next upcoming word must be the do. Okay, so how does it do, like how does it learn? So the left hand side remains constant for this given, like it's fixed for this given fixed input. Let's see the probable output we are trying to make the model learn. And understand there's something called mask, because so we are inputting the entire um we're inputting the entire sentence, that I like to do math, start and end, but it will learn only from the first four, or only from the first three, and that is what is being explained in the later part of the discussion. There's something called mask related to this, and I'll be discussing it. Essentially, masking is nothing but deleting the unnecessary words like do, math, and end, which is not related to, like like which is not related to if you just take the first two words. Okay, so if you want to make the model learn do from I like to, the math and the end will not be required for that. Okay, and that is very important. So our goal is to learn, as I have told you, theta a and theta d. So you input this subset of this sentence I like to, and it's expected to learn do, like the word do. So it's changing the numerical thing, and the mask is presented, so that essentially the entire sentence is presented, like is inputted, and the mask learns that you have to just take the first four words, and then again it's inputted into, like, the function is being, the functions, computes everything, all the jargons, and then after that, what is being outputted is a corpus of all the words and its corresponding probabilities. So we'll see a softmax function is used here, just like the DNN, that first, the finally it's a fully connected layer and the softmax function. So essentially, it's a big length of corpus of all words, like it's a length of the all words. Let's say 10,000 words are there in English language. So it's computes a probability of each one of them, and this is the computed probability based on the weights. So it's the function of the weights, theta e and theta d, and this is the expected probability that it will be do, where it's 1 and rest are 0. Okay, as you can see on the screen. And finally, the loss of this is being calculated using cross entropy, as it's written on the board, and that is minimized using gradient descent methods and other things. That's the basic idea. Okay, and the training is done for a fixed sentence and all such possible subpairs, like this, this, all such subsets of those, so that it learns the next word pretty well. And this is very fundamental for understanding, and that's why this is how the model behaves, as I have shared in the previous one. It should learn in that way. Okay, uh, yeah, that's the basic idea. It should learn in that way. And yeah, so, and finally, if once it learned, the theta and theta d are learned, if you just input the the blue part, automatically will give the output. Okay, based on the probabilities, based on the parameters. Great. Now, this is the aspect of how it's being trained, how the learning happens. The next aspect is, what is the structure? How is this implemented? What are the types of the function f and g? Okay. So this is what is being given in the paper, and I will tell you what is all about step by step in all these things. The main things are, I will explain, is input encoding, positional input embedding, positional encoding. Okay, the multi-head attention and this feed forward add thing, multi-head masked attention, and here the multi-head attention. All these things three are different, and then finally this layer where it will be like how it's computed. We will discuss this thing again, but essentially this 5 6 aspects are really really important. 7 aspects are really important for you to understand in depth, and I think this is where I've struggled and spent a lot of time to get my head around. So so essentially it will start with inputs here, and these inputs are nothing but these words are similarly the words you're seeing here. And let's say you can see that these words is, I mean, I'm just saying that these words is x1, x2, x3, and x4. Okay, and I'm just doing the whole computation out there. So let's see. And yeah, so let's understand this whole thing again and again in very depth, minutely. So what is input in embedding? That's like, there are two aspects here: input embedding and positional embedding, encoding. And let's understand what is input embedding. So let's say these are the words x1, x2, x3, x4. Like onko amar bhalo lage. Like onko is the first word, amar is the second word, bhalo is the third word, and fourth word is lage. And there are two other words that I have told, the end of the statement and the starting of the statement. There are other words also you can consider, like as full stop, comma. You can also learn these things. And there's some token, they are it's called the process of tokenization, and it's some token is assigned to those corresponding words. And but the basic idea is that, but the tokens are categories, character are usually characters. Okay, they don't have much mathematical. So the goal is that the tokens are one dimensional representation in some sense. But what you need to do is that you have to transfer these tokens into a set of vectors. So now it's told that this each of the word are projected into some d model dimension, r to the power d model, this dimension, which is in the paper is taken as 512. So each word is being projected, each word is represented as a vector of some real numbers, a vector in r to the power 512. Okay. So therefore, each word is being represented, like Onko is represented as 0.12, 0.3, and then there are 510 more real numbers. So every such word is being represented as a 512 tuple real numbers, like 512 real numbers vector. But one interesting catch is that are they random? No. So the vectors are, I don't know exactly how it's done, but these two words, if they're similar in, they're similar in meaning and stuff, they are inputting vector, their embedding vector, input embedding vector will be very close by. Okay, will be very, very close by, and that's very important for understanding. For example, you can see here that tissue spoon knife, if they deem if said let d model be 2, so in that case it can represent every such uh, word in this two dimension. You can see the tissue spoon fork knife will be closed by, and orange guava apple mango will be close by. Okay, because they are use or meaning are the same. This is made by some algorithm. I don't know exactly how. Maybe I will learn soon, but this is what I understood from doing some survey and learning from online. And each word has its unique embedding vector of length 512. That is the dimension that is written here. Okay, so each word, therefore x1 is a 1 cross 512 length vector, x2 is a 1 cross 512 length vector, x3 is a 1 cross 512 length vector. And this sentence length that আমি অঙ্ক করতে ভালোবাসি, আমার অঙ্ক আমার করতে ভালো লাগে, so this is a four words, so we'll call the length of the word as n is equal to 4. Okay, so that is a sentence size you can see here. Now if you stack these vectors up, like for the first word, second word, third word, fourth word, and then for n words, it will be a n cross 512 length matrix, right? Which I call xi, that is x set of all words in input embedding. So this is the input embedding of the set of all input words. Now, what is positional embedding? So what is positional embedding is nothing but, understand, our goal is very clear here. Our goal is to take a note of the position of the words in the sentence. It's like noting the position of the words and implementing it as into the X matrix, and that is very, very important. Noting the position of the words in the sentence and implementing this in the X matrix. Now, so understand xi, the X input embedding is of n cross 512. The best possible scenario will be creating another matrix of n cross 512, which can be added to this input embedding matrix. So essentially we want an x cross p, which is of the dimension n cross 512, which will be added to the xi, the input embedding matrix, right? And so that, understand why it's done, so that the algorithm learns to take the information of all the relationship, all the position of the sentence. So this was not previously done in RNN or other like RNN, LSTM, all these things. This window of possibility of the window of reach of in the sentences was smaller. In transformers, it's infinite in size. Whatever you want to, it's n sized. Okay, and that's the interesting part of it. That's a beautiful part of it. So in some sense, it's collecting all the words, information of the words, and also its corresponding position, and we want to form a final matrix representation of it, which is n cross 512 dimension. Okay, so we already the words information out there, but we not need to input in xie this form, this one. Now we want to input the positional information in xie. So understand, each word has a 512 dimensional representation in xi, in input embedding. So correspondingly, for positional encoding, for position we have to input similar a 512 vector length vector to each word, unique 512 length vector to each word. Okay, and it's not dependent on the word, but it's dependent on the position. So the positions are fixed 1 2 3 4 n. So for each position you have to mark one such, for each position you have to mark one such 512 length vector and then club it together to form a matrix. So therefore for each position we need, for each position we need a, we need to define a 101 cross 112 vector which is similar to that in I, but it will include the position information. That's why it will be just dependent on position t and not on the word value, like is it eat, is it do, is it like, is it whatever. It doesn't depend on the word value. What's just the position. So for position t, we are getting the following vector. We are defining the following vector. Its position t, let's say t is equal to, we are defining sine 2 by f1, cos 2 by f1, sine 2 by f2, cos 2 by f2, and it will go on for sine 2 by f 256 and cos 2 by f 256. And you can see that there are two pairs of sine, a pair of sine and cos, and there are 256 such pairs. Hence the length will be 1 cross 512. And this is nothing but related to like now the frequencies are nothing but is defined as 10 to 10,000 to the power m by 256, right? And m is nothing but this, like this suffix out there. And this is assumed as frequencies, and I can give an intuition. There are two. One thing is written in the in the paper. I will tell you that, but my guess is that it's like similar to uh, creating a basis vector, different kind of basis vectors which are independent of each other, and it gives a unique basis vector. And that's the idea. Each such length is a basis vector in some sense, in some dimension, in that dimension, and none of them are related to each other. So that's the fun part of it, and you cannot derive one from another by linear transformation. And so it's uniquely defined the position. That's what it meant. For each word there was unique vector, and for each position there is a unique vector. Now we are adding it up. For each word, therefore, there is a unit vector position, unit value vector, and there is a unique position vector. We are adding it up to get a final matrix. For example, for this onco word, we are getting a this corresponding vector. Vectors onco word, we're getting this corresponding vector. For Amar word, we're getting this corresponding vector. Sine 1 by f1, sine 1, like cos 1 by f1, sine 2 by f1, cos 2 by f2, like this, and similarly for all of them. And we're adding it to xi here, this 0.1 to 0.3 to get a final. It will be also be n cross 512, but it contains both the input value of the word and the position of the word. Okay. But understand one thing, that why it's important. Your question must come, why it's important. As I have told you, it's kind of uniquely. So understand why we define like this, because we have to find such a representation, because we want to add a n cross 512 matrix only. We want to make the computation very simple, so we want to do the addition computation to the input embedding. So to add an n cross 500 length matrix to the input encoding only. So therefore you have to define it like it. You have to define only a 512 length vector. We cannot define it as 1 2 3 4. We have to define it like 512 length vector. Okay. And that's interesting. So now why it's defined like this? Why not 1 1 1 1 1? Why not 2 2 2 2 2? Why not 3 3 3 3? Probably this gives better. It's given in the book that it gives better. They have tried out different things, but this gives better representation. I need to learn more about it. There's also one thing that there's a linear transformation which leads to the translation of this. You can learn about this. I will share the links of those things to the in the description of this video. But basic idea is it's want to create a 1 cross 100 length vector for each word, and it should be unique. So the uniqueness comes from a unique basis idea. You can think of it, and it's like a basis of, it's like making a wave function kind of thing. So the basis kind of thing, that's very important. And uniqueness, and it's a 512 length vector. That's it. Okay, this is what you just need to know. Why it is done, you can learn about it more by more experiments and thing. But essentially, it helps in optimization. It helps in optimization functions, and those optimization intuition comes to those great people by experimentation. Okay, so you and me cannot understand that very easily. We can only understand experiments. So let's take it for their words. Okay, now once we have represented the vector input vector as with both the value of the word. So if you have seen, with both the value of the word and the positional and the input embedding and the positional encoding, it's time to go to the what is meant by attention. Now, attention is really interesting concept. I really liked it. I'm really happy to share this with you. It's really good. So what do you need to what is mean by attention is that we are paying attention to each and every part of the sequence of the words and the relationship of every part with other parts. So it's a word, there is this word, so we are understanding every pair of relationship, each of the pair of the words. So understand the matrix naturally comes up. So the goal is to model and being attentive, model attentive relationship. That's like a word to make you understand between every word pair. And understand to do that, this is the word, this is another word, and the relationship can only map by these pairs, like the elements in the matrix. So therefore matrix come up, and this we do this in the like it is done in the paper in the following way. So understand from the previous input we have got x, which is n cross 112, which is the embedding in some sense, which contains position and value information, and now it's passed through query. Like 3 matrices are made out of it. Now what is the purpose, what are the purposes of these 3 matrices? So I have read in one place, I think it's MathStack Exchange or some Stack Exchange, that imagine that you're putting in some like let's say you're typing in some, let's say you want to watch, like understand the math behind transformers. Let's say you write this in YouTube. Now YouTube will match this whole query with the keywords of all the videos out there. Okay, and then based on this, like now it will try to match that how this q is close to k, which of the q's is close to k, and then based on the videos that you have, so how this, it will try to match how these keywords are close to this queries, right? How the keywords are close to these queries, and based on the videos, like the keywords of the corresponding videos, it will try to give a weight to each such, it will try to give a weight to each such video. Let's say x instead of all the videos, then the query comes in, and it's something different, but the basic idea is this. So essentially it's trying to, what here the query is the same word, and we're trying to understand the same word by the same word relationship within the same pair of words. Okay, we'll see later on when we do the decoder, you will try to understand the relationship within 2 different words, one from 2 different languages, same meaning. But here we understand the relation between 2 same words. Okay, that's why the query comes, the key comes, essentially the key and value should come, we will see later on, should come from a different word, and query should come from another word. But here both the words are same, it's from different word, query is from different one, key and value are from different words, like different sentences. For example, query is from amar onko amar bhalo lage, and the key and values are extracted from I love to do math, I like to do math, and then they are computed together, like how it's done. But let me explain to you the math behind it. So essentially we want to find a similarity between the 2 words, and then finally form an output of it to understand that which pairs of words are related to each other and what score should be given. How? So what is done is that x is being projected to from n cross 512 to n cross 64 dimension by a weight matrix multiplication, which is of 512 cross 64 dimension. You can see n is being projected to the dimension n cross, like each 512 length vector is projected to each 512 length vector is projected to 564 length vector. Okay, in terms of query. In terms of key also, each 512 length vector is mapped to a 64 length vector. So it's a matrix now. It's an n cross 64 matrix, and for value also it is done the same thing. And the corresponding matrices are WQ, WK, and WV. Now understand, we are trying to learn the relationship in all these sentences and words, and therefore these W's are the learnable parameters. These are the theta E's. Okay, these are part of the theta E's. These are learnable parameters. And based on this query, keys, and values, we want to find an attention score between these two sentences. Okay, so what we'll do now, essentially you can see that the attention score can only be, remember, if you are putting a query, it's matching with the keywords of the videos. So essentially the score, similarity score, will be based on some relation with Q and K, some similarity measure, and the best similarity measure of two vectors is the dot product, right? It's cosine similarity. Dot product is equivalent to cosine similarity. So what we do is that we take QK transpose, which is nothing but computing that the ijth element is computing the similarity of the xiq query, the xith query, and the xj's key. So essentially it's trying to find the relationship in terms of the relationship between xi and xj, the xith word with its position and the xjth word with its position information that is contained in both xi and xj, right? And finding the relationship with it, and essentially it's a matrix of n cross n, therefore like n words versus n words, and each element, the ijth element, tells you the relationship, the amount of similarity between these two words, not only in terms of value but also in terms of position. And this is very interesting, and this is learned from the data, from the training port. Okay, so it's measuring the similarity between xi and xj, the ijth element, and this is really interesting. And this matrix is related to something called attention score. This is called the attention score, similar to attention score. Now there are certain things I should tell you. Now after this, it's normalized. This matrix is normalized. Similarity matrix is normalized by 1 by 512, and then the softmax is applied along each layer, along each row. So essentially, and each row you are getting that what is the probability that x1 is related to x2. X1 is 0.1. What is the probability x1 is related to x2? That is the first word with its value and embedding, value and position is related to x1. That is 0.1. What is the probability that the second word, the first word is related to the second word in terms of value and position? 0.1. So, and you see the maximum relationship between zero, like with the fourth word. Okay, just like it's a toy example. Okay, so therefore, by normalizing, we normalize it for optimization easiness, but the math is telling that so this matrix is giving a probability distribution from each xi to other words. Okay, x1, x2, dot x. Here it's x4, but in general it's xn. Okay, and that is being done. You can see this is being calculated by this matrix, and it's a n cross n matrix. So each row is giving that what is the relationship with x1 with the other corresponding words in the same sentence. Now what we do is that now we want to make now we know the probabilities, how x1 is dependent on all of these x1, x2, x4 words, xn words. Now we want to find a final value of x1, right? Final attention score that should be given to x1 based on all these values. And that attention score, that feature, is being measured by, understand, these are probability. So it's 0.1 if you see the first thing x1 is related to x1 with 0.1 probability, x1 is related to x2 is 0.21 probability, x1 is related to x3 with 0.1, x1 is related to x4 with 0.7. So understand that each of those 0.1 should be multiplied to the value. So what is the value? You can think of the value as a, a lower dimensional feature representation of x. So x contains position and word information, position of words and actual word meaning information. So from 200 dimensional, 215 512 dimensional vector, each word is being like those values being projected to a lower dimensional for better computational ease. Okay. Why will we calculate for 512 if we can do it in 64? Now we will tell you why 64 is important in some sense. It's not a magical number, but it's important in some sense for computation purposes. Essentially, it's a similar it's containing similar information as x, like the most important information out of x, okay, which is contained in x out of x. Like it's a projection, the best projection. It's like a principal component analysis. We are taking the most important component, okay. And so therefore, if you see, what's happening is that we are multiplying that probabilities. So 0.1, 0.1, 0. So understand that x1 is going to, let's say, x2, x1, x2, x3, x4, and the probability of them going to 0.1, 0.1, 0.1, 0.7, and from there the value of x1 is v1, the value of x2 is v2, value of x3 is v3, and value of x4 is v4. So to get a final feature representation which contains the information of x, each of the, so let's say, oh, it's a word, let's say Amar, or let's say, yes, let's say Amar or Onko. Okay, let's say the Onko, the first word, and the first word is being attached to all the four other words in some sense, like all three other words in itself, like x1, x2, x3, x4 with some probability, and each of those words have a certain value. So to find the final representation which contains the itself information and the relationship with other variables, it should be contained in this terms of probability and the values, right? So we multiply what? This probability is 0.1 times v1. For example, for the second one, it's done 0.5 times v1 plus 0.2 times v2 plus 0.1 times v3. You can just see the second one. Essentially, it's creating a attention for it's an attention vector, like a feature vector for each of the word after creating the attention score and all these things. And this is very, very important. This is super important for understanding. It's a weighted value of average. So this is like giving a score to each word, okay? And it's fun. And you see, it's n cross 64. It's a 64-dimensional, a matrix, which gives score to based on the position, on meaning of the word, position of the word, and the relationship with other words. It contains all the three information in this, okay. And a single information is given by a 64 length vector for each word, and it's stacked up in this whole thing. And this is being computed in this way, that softmax, that initial probability matrix times the value vector with value matrix, okay, as you can see. And it's create a z, we call that, that matrix z, n cross 64. Understand the three important things. The softmax part is measure of importance of each word with respect to the other words. V is nothing but a shorter word embedding representation of the, of the x in R to the power 64, and that is nothing but the weighted average of values, which is nothing but the final importance of each words, which contains all the three information: position, the value of the word, and the relationship with other variables. And the whole thing is learning, and it's based on all these weights, like all these parameters, w, k, q, w, k, and wv. That's why it's, so you can see how much information can be stored in this, and that's the best part of it. In this small matrices, everything information is stored, and that shows us that how language is redundant, how much language is redundant. We can predict language much more easily than we should. That's why all these shorthand notations work so well. Okay, so now Since this is done, so single attention is done. Now now the main part is done. Okay, the next parts are pretty simple stuff. It will be very quick. The main part was a single attention head and the intuition of it. What's the meaning of that? So you can see, let's focus on this part. This part we have already seen. uh, the embedding part. Now here it was xie, here it was xp, and it goes as out as x, and now it enters the multi-head attention. Now what is multi-head attention? Let's understand. It's based on, you can understand it by the nomenclature, you can understand it's like a multiple attention thing. Okay, so let's understand how it's done. So what is done is simple. So x is the input user, as I've told you right now, and the input is, now what we are doing is that, remember this 512 was 64 into 8. So remember that we are actually projecting the five, each word is projecting of each word is 512 dimension. It's projected in each z in 64 dimension, right? And 8 of them are similar. So eight such attentions mechanisms are done, are being calculated. So it's a, each zi are certain feature representations, of each of those such relationships: position, value, and the relation with other, the other words. Each such zis are such relationships. Okay, each such zis are such, such matrix of relationships, and all the informations of the entire x, and there are 8 of them. So 8 into 64, so it's a 64 dimensional. So word is being each word is being projected to 64 dimensional, 64 dimensional short representation, which are called multi-attention head. And these are concatenated together, the z ones, in a horizontal way, column wise, and which gives you the final representation of 9 cross 512. Okay, and which is multiplied by w naught, another vector of 512 cross 64, which again boils it down to n cross 64. So the final output is z star. Okay, this is the basic idea. The final output is z star, which is the final representation of the multi-head out of this multi-attention head of this, where the input is the x vector, x matrix. Okay, so each 512 representation of the, the vector is being inputted into 64 such, is being expressed as 64, projected in such 64 dimensional space. 8 such representations are there, and then finally they're concatenated together and a weighted average is taken of each such vectors. The weights are being learned by the model, okay, by after training. And the weighted average of those 64 dimensional thing, it's essentially you're taking the mean in some sense, or it's been learned by the model, but essentially a weighted average of those vectors are 10, and finally a 64 dimensional vector is being learned out of this x vector, which is like, you can see how the amount of work goes, how the amount of information about the relationship of the words or the interrelationship of the words are being stored here by multi-attention heads. So you can say instead of this 64 dimensional 864 dimensional, you could have just taken one big n cross 512 dimensional thing. I personally think probably then the amount of richness of information, this parallel computing thing would have not given this one series computing thing would have not given the amount of information this parallel computing gives. It gives multiple dimensional views and taking the average of it. Okay, so I think I personally think that they are not equivalent, but they can be equivalent. You can probably say that, or probably there can be some computational aspects out there. Okay, so this is one question that I didn't answer myself right now, but it seems that parallel computation seems much more, interesting, much more rich information, because it's in all the dimensions are 8 different dimensions are taken. Okay, now understand what's the parameters. The parameters are wk, you can see for each 8 of them. So wki, wk, zi's are 8 of them. So for each I, 8 of them there. So 8 such, 8 into 3, 12, 24, and plus 1 the w naught here, such parameters. Okay, so 25 parameters here, like matrices to learn. Great. And this is a multi-attention head which is based on the attention only, and then it's being added and added and normalized. So what is an added and normalized? It's nothing but, and there is something called residual. You can see this. So here is it's entering x here, and x is entered here, and then this goes into the all key q and v, and the output here is z, and it's the z and x are added. So let's call it z star. I call it z star probably here. I don't know why I called it z star. So it's not z star, essentially it's z. So this z, oh no, not it's z star actually. Sorry, because the z star is this final after multi-attention head. So this is the z star. The z is input from here. Like z is like the z is the input to the multi-attentional head. Okay. No, not really. Z was the single attention head thing. So multi-attention head gives such different eight such z's, and we concur it together, get z star after the w naught multiplication. So we are getting a z star, and we are getting an x out here, and we are adding them and then normalizing it in certain way by centralizing and normalizing it. These are being done as it's similar to batch normalization, so that the algorithm converges easily. There is no optimization, other thing issues. It's actually like batch normalization in deep neural networks. Okay, this is a multi-attentional head, and this is add and normalization aspect. Okay, so and then let's see the final layer out there, final aspect out here, the encoder structure. So if you see, this is, so let's revisit. So here are the words, here the xi input embedding, the positional embedding, and then we get the x, then we get the z star, the concurrent version, and then we, okay, by the way, this add and normalization has one thing. This is called a residual structure. So whatever has been learned, not learned in the z star, we are adding x again so that it's learned again. Okay, we don't lose it, and we'll see, we will run this n number six number of times, so we are not losing any information, and this is a very interesting step. So this adding a normalization helps you in regaining unlearned feature. So it's called residual. That's why it's regaining unlearned feature. And then, okay, so then let's finally revisit the encoder structure. The encoder structure, as you can see, we have the xie, xpe, which gives in x, and then z star comes in, and then we have the residual structure, which is the x structure, x plus z star gives x plus z star. We normalize it, and then we feed onto this feed forward network. Feed forward network is nothing but a sequential linear network, like fully a linear network, fully connected layer, and a ReLU, and then a linear network. And again, which is this z x plus z per is input into that. There are also weights out here, which are learned, and then it's again added and normalized, which is called x curl n cross 64. The output is n cross 64. Okay, I have checked the code. The output is n cross 64, and this is done n number of times. You can see, which is n equal to 6 in the corresponding paper, and finally again the output is n cross 64, because input is n cross 64, output is n cross 64. So uh, yeah, so that's the part of it. And am I doing it right? Just let me check. The x was n cross 512. Okay, so probably, so I have to check once. Probably there's a small mistake out here. Either it is n cross x, essentially it's either n cross 64 or it's n cross 512, because understand, it's again inputted into uh, another layer, another layer here, which is again inputted in another layer here. So the input here x should be n cross 112. So I think it should be personally n cross 112, and the final output probably should be n cross 512 or n cross 64. N cross 64 will make some sense. We will check it out later on. But I think personally it's n cross 64. When it's like out of the final layer, it's n cross 64, and the other layers it's n cross 512. But again, I have to check. It's my hypothesis, but again, I have to check it later on after this. But I hope you understand the idea. Okay, so coming back to the encoder decoder structure, if you want to revisit, I already explained it to you. So now understand the output of this, the X curl, let's say, after 6 iterations, it's being imported into the decoder portion. So let's try to understand the decoder portion in a optimized way. So the decoder portion has three important ideas. That is the masked multi-rate attention, the multi-rate attention, which takes input from decoder and the encoder, and the final part, okay, which is very easy and it's repetitive. These two things needs some extra insights. So let's talk first about the masked multi-rate attention, and it's very interesting. Why it's needed? Understand, if you remember in the model, that here, if you remember, I have explained to first that here we are learning shifted words, okay? And also, as I have told you, the mask is present here. It's, for example, you want to predict, you want to learn the factor that I like to do. The do is only dependent on I like to, and not math and end. You understand? So let's say you want to predict the do, you should make sure that the do part is only dependent on I like to and start, and not math and end. Okay, this is something you should make sure it happens. Okay, and that is very important, and that is done by mask. So let's go ahead and check it out. How it's done. So essentially it's a shifted model. That means it starts with start and not I. So if you input the start, the model will probably learn to predict I. How to do that? So if you input, let's say I like to do math. Let's say if you input I W1, Y1, Y2, Y3, Y4, and Y5, I like to do, the math will be the output. Okay. Or let's say when you are trying to train Y5, okay. So let's say you want to train Y1, Y2, Y3, Y4, that I like to, and you want to do want to transfer do into the as output. Your input is I like to, and you want to transfer do into the output. You must make sure that it's not dependent on x6 and x7. And how to make this happen? Essentially, it's done by, so if you remember, it's essentially understand the relationship between this sentence, in this sentence, and the sentence is, you can see its sentence is this. In this case it's 7 cross 7, but it's n cross n. The similarity matrix, that q3 transpose 512, the qtr corresponding to this decoder aspect, the output sequence, output words. But understand that you don't want a relationship in with 6 and 7 with the rest of the words. So what do you want? You want that in the probability, when you do softmax, it should be 0 0 0 on this, all the relationship with, so this y1, this portion tells you the relationship with y1 and y6. This portion gives you a relationship with y1 and y7. So therefore, this two will not be important at all in training, but this, the most important part will be this region. And you want, in the probability thing, you want them all to be 0. So how do you make sure, how do you make sure that it happens? You add a something called a mask of infinity and zeros, and add it to it. All these finite things will be same, and this portion will be all infinity. And how does this help? When you take the softmax, the infinity will become minus infinity will become, so all this portion will become minus infinity, and when you take the softmax, it will become 0, and that's the best part of it. Okay, when you take the softmax, the probabilities will become 0 because you do the exponential of minus e to the power minus infinity. And therefore, after doing the softmax to this is a mask. This is a mask. After doing softmax, you get zeros, and every single time you give a word out of a sentence, every single time you give a word out of, like a sequence set of word out of a sentence, it automatically gives a mask depending on till which words you are giving. Okay. Excuse me. And yeah, that's the whole part of the mask idea, and it's a decoder mask multi attention. It's the same thing. uh, yes, and everything is same. Okay, all the zis and all those things are same, and uh, the embedding also same. So it's like the outputs are embedded and positional encoding is done, and then this is the multi attention is done. But another multi attention is done with the masked way so that you do not learn the unnecessary relationship with the unnecessary words, the later on words in the sentence. And now out of this, the input, if you remember, out of this, it was the output was here. It will be some z y, which is n cross or m cross 64, depending upon what length of word you're learning in the output. It's m cross 64. Okay. So now now the encoder decoder self attention, where it's taking the input of this. Uh, just let me check once. It will be 64 only. I did a mistake out here. Yeah, let's call it y64, zy64. So understand that from the encoder side, you're getting the input of the total learned, like total feature of the end of this of the word we have given. Let's say onko amar bhalo lage, that's phrase, and that's contained. The total information is contained in this, and the total information is contained in this zy cross 64, m cross 64, the length. Yeah, it already went in the multi attention of the. Yeah, so therefore the output should be out of the multi attention. If you remember, the output is always z, which is of z star, which is of n cross 64. So essentially it will be zy, which is of m cross 64. So you have an n cross 64 matrix from the encoder, and the output matrix z y m cross 64, the m words cross 64 out of this masked multi attention head from the decoder part for the output part. So it's from the input, from the output, and then these are inputted, taken the input into this multi-attention head. But the multi-attention head works similarly. It calculates the key, the query, and the value, but it calculates in a different way. Understand, now we have the opportunity to use that idea of query, key, and value, and understand that we want to learn certain weights out here, so that the key is from the encoder part. So the output is like the query you're writing. Let's say in Google you're writing YR. So these are the queries, and automatically you're writing down in the Google YR, automatically you get suggestions, right? The suggestions are the values, the best values out there. So the query should be from the decoder place, because the output thing, like, and the encoder contains the keys. So we're getting the keys from the encoder, that okay, why are this are related to, it's also, you can think in terms of the YouTube thing, related to curious or certain words, which we get those keys out there. Okay, we get those keys out there, and based on these keys and queries we form, and also the values out there. Now we will see why the values of the, because we are interested in the values of the learning from the values from the encoder sequence. Okay, the relationship, but also we'll see why values also of the encoder comes up mathematically. So to understand the relationship of the encoder and the decoder, we try to find the similarity of the query of the decoder and the key of the encoder, okay, which gives QD and KE transpose, which gives M cross 64 cross 64 cross N, okay. And probably this will be 64 cross 64 also again. And therefore, the width, length, width, dimensional width should be different. And therefore, understand we get a M cross N similarity matrix, which tells you the relationship with, let's say, M x1, x2, xn. So it's M cross N, so X and xn. So its relation, the ijth relationship is nothing but the relationship with the ith output sequence with the jth input word, ith output word with the jth input word, okay, with the mask things and on, okay, with the mask things and all those information. Ith input sequence and the jth output sequence. So Jij is nothing but the ith output sequence versus the jth input sequence relationship or similarity. Okay, this is similarity matrix, and this is being multiplied. So this is M cross N, and how this Z is calculated, which multiplied the value vector. Now the value matrix is should be N cross 64 to make the dimensions clear. Okay, so therefore it's QD KE transpose VE when you comparing the encoder and decoder, and this gives the similarity matrix I have shared with you, the Z after. But remember that why not a VD? Probably because you will not get it's like the structure of it mathematically. Okay. Also, you know, learn the value of the encoder sequence, not the decoder sequence, because that's what we are getting here. You have to express in terms of the encoder sequence. Okay. The output sequence ka value will be expressed in terms of the encoder sequence ka values. That's how the relationship is learned. Okay, and that's the best part of it. So therefore, that's how we get the Z part and Z part of the decoder multi-head. So the encoder decoder self attention, and both the input are taken together. Okay, and yeah, this has been long, and but I hope it helps you in learning. And then finally, this everything is done, and then finally after this, in the last step, we do this 6 times, and then we get to the probabilities. After the probabilities, like how do the probabilities again done is linear, ReLU, and linear, just like the linear portion of it, and then it goes to the softmax just like it's done in deep neural network. And then we take the corpus of all words and we see the probabilities in it, and then we take the word with the maximum probability. Okay, and then as I have told you in the previous one, while training we have the computed probability from the weight matrices, and we have the actual probability where we put one for the expected outcome, and we learn the difference between the cross entropy, and we learn the loss by minimizing it by cross variance. So we get the loss out of it. We sum it over all such tuplets, all such inputs and output sequence ka set, and we sum it over it. Okay, that's how the cross entropy is calculated. It's like my summation over all such input sequence, and for each input sequence, understand the output sequence belongs to certain function, like pieces of output sequence, like shorter, like big pieces like this. For each of these input sequences like this, because for input sequence only one, for each input sequence there is only one sentence which means exactly the same, or multiple sentence maybe. So each such output, start I do, start I do, like, so something it's all the subsequences are being captured as output sequence, and then the minus log of the, the probabilities, and probabilities, the cross entropy minus the is calculated. Okay, and that is minimized, the loss is minimized. That's it. Okay, so that's the loss function, and the final review is this. It's the hyperparameters, if you see. Okay, final reviews is that first you input the word sequence sentence that is being transformed into a matrix of n cross 512, which is called xi, Then it's added to the matrix by positional XPE. It's also n cross 512. And then this is then the final key Q query and V is and multi attention. And finally Z is out, which is the similarity matrix. The attention scores are being delivered, and it's the residual thing is added and normalized to X so that we don't forget it. And then it's again to the feed forward network, the linear, ReLU linear. Uh, sorry, in this feed forward linear, I think it's a total linear network, and then it's softmax. Okay, it's like a totally fully connected layer, and then it's softmax. And then in the feed forward network, this is the um, so we know what the feed forward network comes out. Then we again added normalize. We run it 6 times, and probably the output will be some X curl n cross 64, which is inputted in the encoder decoder region. Now for the decoder, we get again YIE with the masked version, masked, and not the mask here, YIE, and then again YPE. Both are M cross 64, M cross 512, N cross 512, and it's inputted here. And then again, the key query and value are being added, and with the mask thing, which gives you again the attention thing. And finally the Z comes up, it's again in cross 64. So n cross 512, sorry, the n cross 64. And then again the X is added. I think there's a small error out here where I have talked about the X plus X star, um, adding a normalize. The X was essentially n cross 512. I think it's added to the actual Z and then normalized. Okay, actual Z and then normalized. It's both are 512 dimensional, and that's why exactly it's done and then normalized. Okay, and then the weight comes up. So there's a small error. I apologize for making this error, but I hope you understood the basic idea of it. uh, and yes, so then yes, so then again it comes out with the final attention thing. And it again again the same thing happens, and there's a self attention, the residual layer, which out of which the whole thing comes out after normalizing it. The main thing happens that here X curl comes up, here Y curl n cross M cross 64 comes up, and adding and normalizing it, we get a final layer. And what we do this attention thing, and then we do the feed forward, and then a final probability output comes up. Okay, and then the whole loss function is done. And yeah, so I hope okay, so coming to the hyperparameters, the n is the total number of how many iterations are done. This thing is iterated 6 times, as you can see. Left hand also iterated 6 times. Then a D model, that which dimension the words should be projected. And then the feature vector 64, like if you remember, it's rich, like two things are there. One thing is the query and key 64 understand, because it was Q K transpose V. So even if it was, let's say, n cross 64 and 64 cross n, so therefore the query and key should have the same dimension, but here V could be n cross 79 also. So the dimension of the value can be different, okay, where it's being projected. So therefore the Q and query should have the same length, and value can have different length. So that's a hyperparameter, you can play around with it. And parameters are all the weight matrices plus the feed forward and all those neural network matrices, where you can um, actually, you know, like, which is there for every iteration out there. So thank you guys, and I hope it helps in your learning. I know I fumbled a bit here and there, Uh, but for example, I am not really happy with this last moment of change of X thing. But I hope you understood the whole thing overall. Here, the X is added to Z and not Z star, and then the W naught is done and then normalized. So please make this thing sure, and I apologize for this last small error. But I hope this work of mine will help you in learning, and I hope it will help you in understanding the transformers in a better way. So thank you for your time. Thank you for watching this video. And yeah, thank you and have a great day ahead. I hope you will learn more and find more joy in learning more about computer vision, deep learning, all these interesting ideas. So thank you and have a great day ahead. Bye bye.